Hey guys, today we're going to be talking about horizontal asymptotes and how we can get at them via some calculus. These will be important in evaluating the end behavior of certain functions, which will be important in everyday contexts, such as what's going to happen with carbon emissions, what happens to average cost as we let stuff go out to infinity, production go out to infinity, and so on and so forth. So, let's get started. So let's get into some notation. We will be coming up and digging up limits that came up in chapter 1. So without further ado, given a function f of x, the limit of f of x as x approaches infinity is just what happens to your y value as x grows infinitely large in the right-hand direction, as x grows towards positive infinity. Similarly, the limit of f of x as x approaches negative infinity is as above what happens to your y value as x grows infinitely large to the left, meaning in the negative direction. Now, just as before, these limits do not have to exist. These are only defined if we settle down on a single value, a single finite value for that matter. There are definitely cases where these do not exist. However, we will be studying oftentimes the cases where they do exist. So all of our limit tools will be coming into play again. Based on our intuitive definition from last slide, let's go ahead and try an example. Here I've drawn up a perfectly good function f of x in red. Now let's go ahead and evaluate the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. To do the first one, as we approach infinity, that was just what happens to your y value, what y value you settle on, as x tends towards the right. If this graph is accurate, it looks like we kind of start to hug this bottom dotted line of y equals negative 3. And in fact, that's our limit. The limit as x approaches infinity of f of x is just negative 3. Similarly, to evaluate the limit as x approaches negative infinity of f of x, we just figure out what y value we settle on as x goes towards negative infinity. Looks like it settles on the dotted line of y equals 2, so in fact the limit is equal to 2. That's our intuitive definition for how to evaluate these limits. As an example of one where you do not exist, if you allow me to change up f of x to be this function right here, so on and so forth, kind of like a sine function towards the right, our limit as we approach positive infinity would no longer exist. And we would say does not exist. The reason it does not exist is because, yet again, we're not settling on a y value. For instance, as I go to infinity, there are definitely x's where my y is up here. And there are some where my y is down here. Since I cannot find a common y value to settle on, the limit would not exist. The limit as we approach negative infinity would still exist because we do settle on a y value out here. Now, as you might have noticed in the previous example, these limits as we approach infinity look a lot like horizontal asymptotes. And indeed, that is actually how we define horizontal asymptotes. If the limit of f of x as x approaches infinity equals some y value L1, and the limit as we approach negative infinity of our function equals some y value L2, then the lines y equals L1 and y equals L2 are called horizontal asymptotes. This is just a fancy way of saying, hey, these lines are horizontal asymptotes. Now, interestingly enough, you may have 0, 1, or 2 horizontal asymptotes. As an example, we'll have the following three pictures, three graphs. The first one looks like a graph of y equals x. This one doesn't have a single horizontal asymptote. The reason being, there's no y value as I approach infinity, or as I approach negative infinity that I ever settle on. You have to settle on a y value to have a horizontal asymptote. So none here. The middle picture, it looks like I finally settle one on a y value as I approach negative infinity. As I approach positive infinity, I never land on a single y value. This gives me one horizontal asymptote. Lastly, if I have this picture right here, I definitely have two horizontal asymptotes. As I approach negative infinity and as I approach positive infinity, I settle on two distinct y values, giving me the two asymptotes that we're after. Now let's talk about how we can start to do an algebraic approach to these limits as we approach infinity. Now we need an algebraic way to handle infinite limits. In the upcoming slides, we will actually figure out some shortcuts for rational functions. However, we'd like to be able to justify that in some grounded math. So, the biggest thing that will help us is if you divide a finite number by infinity, you become zero. Think about a family reunion where maybe you got a big family, you got 100 people there. However, let's actually expand that a little further. Let's say you have an infinite family, and you have one pizza that's split between everybody. You will get nothing. You will get absolutely zero of a slice if you divide that pizza by infinitely many people. That's the way to maybe remember this. Now, if we're doing limits as we approach infinity, we're actually going to approach it the same way that we did regular limits. We're just going to try plugging in the number, a caveman approach. Well, when you plug in infinity, there's one small caveat. If you get infinity over infinity, that becomes an indeterminate form, meaning more algebra is required. The way we're going to handle this algebra is kind of the same way we did earlier, by factoring. The helpful thing to do will actually be factoring out the highest power. And what will be left over are a bunch of things, either constants or things divided by x, which we can utilize this fact. So let's try 3 quick limits. What about the limit as x approaches infinity of 5 over x? Well, yet again, let's just try plugging it in. 5 over infinity. Well, if I ever divide by infinity, a finite number by it, that just becomes 0. So that actually cancels out to give me a limit of 0. Simple. How about the limit as x approaches infinity of 10 times x squared? Well, let's plug it in. This gives me 10 times infinity squared. Well, infinity squared, that better be infinity. You times it by 10, yeah, it ain't getting any smaller. This will actually be infinite. Another way we could say this is we could say that the limit does not exist. Last but not least, let's try 5x squared divided by x squared plus 1, taking the limit of that function as we approach infinity. If I were to plug in infinity, I would get 5 times infinity squared divided by infinity squared plus 1. Which, because infinities ain't getting smaller, we would have infinity over infinity. This is an indeterminate form, meaning more algebra is required before we can evaluate. In that pursuit, what we're going to do is factor out the highest power of x. On both top and bottom, that turns out to be an x squared. I factor out an x squared from each. X squared times 5 on top, might seem silly factoring, but stick with me, divided by, factoring out x squared down here gives me x squared times 1 plus 1 over x squared. Remember, if I multiply back in by x squared, I better get what I started with. That's why we get this 1 over x squared in the bottom here. Now, we have an x squared on top and bottom. And in fact, we can cancel those. Cancel, cancel. This leaves me with the limit as x approaches infinity of just 5 over 1 plus 1 over x squared. And now I can try plugging in again. If you don't mind me bringing this up here, give me a little bit more room, we would have 5 over, plugging in infinity, 1 plus 1 over infinity squared. Now the powerful part about doing this is notice what happens to 1 over infinity squared. If you divide a finite number by infinity, you become 0. So all that we're left with is 5 divided by 1, or just 5. Now in practice, if we can use some shortcuts, that's a great thing to do. However, we always want to be able to justify it with the algebra. Now, without further ado, let's get into some shortcuts for rational functions. Now that we have the algebraic tool to actually evaluate a limit, utilizing that if you divide by infinity, you become 0, let's talk about a special class of functions, rational functions. So let f of x equal p of x divided by q of x, where p of x and q of x are polynomials. Recall that the degree of a polynomial is just its highest power. We're going to have the following shortcuts based on the degrees of p of x and q of x. The first shortcut will be if the degree of the top, p of x, is bigger than the degree of the bottom, q of x. If this is the case, then we actually have no horizontal asymptote. Think about this rule as if the top is bigger than no asymptote horizontally. For example, let's consider the limit as x approaches infinity of x cubed minus 1 all divided by x. Remembering our algebraic shortcut, since infinity over infinity is an indeterminate form, what we have to do is factor out the highest power. I factor out an x cubed on top. That leaves me with a 1 in the x cubed spot minus 1 over x cubed. Keep on thinking that when I factor out an x cubed, what do I have to multiply in by to get what I landed on? That's why I have a 1 over x cubed right there. The bottom seems a little silly to factor out, so you could write it as x times 1 if you want. This allows me now to cancel some powers of x. For instance, I could cancel out 1x. This leaves me with the limit as x approaches infinity of x squared on top times 1 minus 1 over x cubed. All divided by just regular 1. Now if I plugged in infinity to this, it's weird to try to talk about plugging in infinity, but if you conceptualize what happens, we would get something along the lines of infinity squared times 1 minus 1 over infinity cubed, all divided by 1. But remember that this cancels to 0, so we have 1 times infinity squared, which is definitely infinity. Therefore, since we do not settle on a finite y value, this thing has to be finite to exist, we would say that this thing does not exist. Therefore, there is no horizontal asymptote for this function, since the degree on top is bigger than the degree on bottom. As a second shortcut, let's now consider if the degree of p of x, the top, is less than the degree of q of x, the bottom. In this case, if the bottom has a bigger degree than the top, then we have a horizontal asymptote of y equals 0. So, horizontal asymptote of y equals 0 if the bottom is bigger, and that's what you should be thinking. For a quick example, let's evaluate the limit as x approaches infinity of x plus 200 divided by 3x squared minus 1. If we want to justify this algebraically, because we could just use the shortcut, degree of 2 bigger than a degree of 1, therefore horizontal asymptote of y equals 0. However, algebraically, what we could say would be by utilizing our trick. Factor out the biggest power. On top, that's just an x, and we're left with 1 plus 200 over x. On bottom, the biggest power is an x squared. So I'm left with x squared times 3 minus 1 over x squared. The reason this helps is because we can cancel out now 1x from each, leaving me with the limit as x approaches infinity of 1 plus 200 over x divided by x times 3 minus 1 over x squared. Now if we go to plug in infinity, what we're left with here would be 1 plus 200 over infinity divided by infinity times 3 minus 1 over infinity squared. Now there's a lot of infinities going on here, but here's the nice part. Remember, if you divide by infinity, you become 0. That cancels to 0, and that cancels to 0. This leaves me with 1 over 3 times infinity. Now 3 times infinity is still infinity, so we have 1 over infinity. But remember what we just said. If you divide by infinity, you become 0. So this thing cancels out to 0, leaving me with an answer of y equals 0 for my limit. Yet again, since now we have this shortcut though, as you just compare the 2, the degree of the bottom, to the 1, the degree of the top, you could say horizontal asymptote of y equals 0. This is all just justifying it. Now the last case that we need to consider for rational functions is what happens when the degrees of the polynomials are equal. If the degree of the top, p of x, equals the degree of the bottom, q of x, then our horizontal asymptote will actually just be given by the ratio of the leading coefficients. The leading coefficients, recall, are the numbers attached to the highest power. So given this function down here, 5x squared minus 3x divided by 2x squared plus 1, just by using our shortcut, looking at the degrees, 2 and 2, we notice that they're equal, and we could actually jump forward and say that our horizontal asymptote is the ratio of the leading coefficients. Our leading coefficient on top is 5. Our leading coefficient on bottom is 2. And in fact, that will be our horizontal asymptote. If we wish to justify this, we could yet again apply our algebraic rules to these limits. For instance, if we go ahead and factor out the leading power, x squared, on top, leaving me with 5 minus 3 over x, and x squared on bottom, leaving me with 2 plus 1 over x squared, we see that we can actually cancel out the entirety of them. And the x squareds will cancel. This just gives me the limit as x approaches infinity of 5 minus 3 over x divided by 2 plus 1 over x squared. Plugging in infinity, we see that we land on 5 minus 3 over infinity divided by 2 plus 1 over infinity squared. But then recall that if you divide by infinity, you become 0. This goes to 0, and this goes to 0, leaving me with 5 on top and just a 2 on bottom. But yet again, you could have just looked at the leading powers, 2 and 2, said they're equal, and then just taken their coefficients, 5/2. That will be your answer. Hey y'all, thanks for tuning in today as we talked about horizontal asymptotes and how we actually mathematically define them. As a quick recap, what we discussed today was limits as we approach plus or minus infinity. These were just horizontal asymptotes. They were not obligated to exist. For instance, as a limit, that is defined only if you actually settle on a particular y value. If you bounce back and forth, you might not exist. We got into some algebra as to how to evaluate them, utilizing yet again just plugging it in using the caveman method, or by having to do some factoring if we ran into an indeterminate form of infinity over infinity. Lastly, when given some rational functions, we got some shortcuts. For instance, if the degree on top is bigger than the degree on bottom, you didn't have a horizontal asymptote. If the degree on bottom is bigger than the degree on top, your horizontal asymptote was 0, and if the degrees were equal, then you had to take the ratio of the leading coefficients. Hopefully this was a little bit of a blast from the past with limits, and next chapter we're going to be moving on to more derivatives, this time covering exponentials and logarithms. Thanks y'all.